question today, is bigger data really better? So, hey, we're all part of this wave that's happening now, which is called big data. We're pretty sure the data part is valuable. What about the big part? How essential is that part? Warning slash potentially positive, depending who you are. I'm CTO of Skytree, but also a professor of machine learning. So I will attempt to throw in something for everybody, whether you're the on the business side or on the technical side. I will have my story in both pictures and math. Ignore the math if you want. Ignore the picture if you want. So now, hopefully, so what I've observed is some of these basic things are all very simple conclusions in a way, but can't always find them in textbooks even. You can have 3 PhDs, you won't find it in some of these things, unfortunately, a textbook. So hopefully there's something useful in here for some people. So is it necessarily better? Who thinks maybe big data isn't necessarily better? Show of hands. Okay, who thinks it's definitely not better? All right, no one wants to take a shot on that. So if it's better, if so, when? And I think it's clicking by itself. Can I control it with this?
Yes. Pick the freeze button on top.
Yeah, I'm not hitting the button and it's clicking. Okay.
That hasn't worked in this room all day.
It's going to be. I'm not touching it at all. Okay. I swear I'm not touching it. Okay. What makes it click by itself?
Shouldn't be unless somebody's gotten on my frequency.
Okay. Okay. So, then the last part of it is, even if it's better, is it really possible to realize all the possible gains? So, first, just establish the basic link between bigger data and bigger value, business value. So let's start with your high-value prediction problem. So you're highly paid, either CDO, Chief Data Scientist, in charge of some business problem that's high value. Each of these things in many companies is often the highest cost problem in the company's way of doing business. No doubt about it, high value. Okay, so now your job is to make more money or save more money for the company. If you're treating it by ML, then that boils down to, it's a simple conclusion, better prediction accuracy. They're directly linked. To see that, so take any kind of problem like a fraud problem or lead scoring or detecting failures in machines. You have some cost. You have a matrix of how many times did you call, let's say, a fraudulent transaction a non-fraudulent, and how many times did you do the opposite, and so on. And there are corresponding costs for making errors in either direction. Now, of course, it's not obvious sometimes how to represent these costs, but in principle, there is one, and therefore there is a direct connection between the getting these errors lower and direct dollars. Okay, so pretty simple. Now, there's a lot to this, of course. All of these things lead to entire other talks, but that'll be later. So, and in fact, one side topic is if you're really doing this right, you directly optimize for this kind of quantity, which is not often done. Okay, now here's the main kind of framework we use. Now, this is the most mathy slide, but that big ball right there, that's your enemy. The big black ball, that's all of your predictive error, whatever your problem is, fraud or whatever. And that's your, we call it excess, I call it excess error on this slide, because this is, there's some base level of error that you'll always have, and that's due to however good your data is. If you haven't collected data of the right type or whatever, then you have a certain, whatever data, you have some error. It's generally non-zero. So the best you can do, and that's sometimes called the Bayes error, it's the best you could possibly do. So you're trying to reach that error. All right, and then these three sub-balls are the three, and only three, that's the good news, sub-sources of error. And so all you can do, essentially, to reduce your error is treat one or more of these three sources of error. Okay? Don't worry about what the math is exactly, but just at a high level, we will focus on the middle one, the purple or pink one, which is using more or less data. That is one of your basic controls for error. And then the other two, one of them, the blue one, is the one you most naturally think of. It's, do I use a good model or a crappier model? Okay, and most of the art of machine learning that people talk about is up there. And then the gray one is not talked about enough, but that's having to do with whether you've found the right parameters for your model. Now, all these fancy models, the ones that are generally used to get high accuracy, they have many knobs. And the extent to which you've tried enough knobs in the right parts of the space, that contributes to that error. Okay? So that's the reason I like to look at that picture is it tells you basically everything you can do. There is no more machine learning. So, but the main point is that the training data size is one of the main determinants of your model's predictive power. It is a lever you always have. You're driving a car, you only have three controls. You have gas pedal. Data size is like your gas pedal. Maybe you have your brakes and you have something else, gears. Okay? Okay, of course, the next conclusion is that from your basic statistics class, which you may have taken, and you only need that one class to know this, which is you find out things like that first little equation there, the law of large numbers. You know, it's kind of what you'd expect. Yes, more data, more predictive power. So this is an example you may have seen. This is coin flips, so let's start simple. If I have a dirty old coin that I found somewhere, I'd like to know, this happens all the time, I'm sure, to people. You'd like to know exactly what the probability of heads is. Well, you flip it 10 times, you'll have one estimate. You flip it 1,000 times, you'll have a better estimate. And the quality of that estimate goes up with the number of flips. Okay? Now, the interesting, or one observation is that you can actually quantify the rate at which your error goes down with the number of data points, which is the number of flips, and it's a 1 over root n type behavior, okay? So math tells you how your accuracy is related to the number of data. But you will tell me, yeah, we're not doing coin flips anymore. We're doing complex problems like fraud. So next question is for realistic high-value models, how do things work? It does get more complicated, but the main upshot is when you move to more sophisticated models, you need even more training data, and that is intuitive, perhaps, but it can be quantified as well. some ways. Somehow it has to do with, you still have this kind of dependence on n. You have in here this thing we call the VC dimension. It's some kind of measure of how complicated or expressive the model is. Okay, now all the kinds of models people are interested in, kind of for these more high-value problems, are going to be things like, they're going to be non-parametric methods. You may or may not have heard this term, but this captures all those kinds of models you hear about. These are, and many of you use. So things like gradient-boosted trees and random forests and support vector machines and nearest neighbor and so on, and neural nets. Okay, so the key is that if you remember that blue ball of the 3 balls, the blue one, which is how fancy is the model, all of these kinds of models can make that error go to 0. 0 with enough data. So that's what non-parametric means for almost any kind of data, near arbitrary assumptions on the data. Okay, so that's magic. If you could say, if you could ask, what is the one main piece of magic of machine learning? It's that we can make that go to 0, as opposed to classical statistics, which are simpler models. Okay, and then from the standpoint of how much data you need, this expression, don't worry about it if you don't want to, but it's basically saying that the growth is slower than in the simple coin flips model. You need more data. And this D thing, D is the dimension, which is somehow the degrees of freedom. Okay, so it's highly related to this next conclusion. So your dimension, at least naively, is your number of columns, right? Your number of data points that I'm talking about is your rows, typically, in your data table. And then what about the number of columns? Well, roughly speaking, if you imagine that you might, if I add some more columns, like I add some social network data, eventually you can translate to more columns in some table. I add some text data, might be some more columns. I add, transaction data. So more data sources, roughly speaking, generally add more information, as long as they are somehow complementary to each other. But very generally speaking, when you add more features, you add more accuracy. You give the model more ways to win, more expressiveness. So you can, it's mathematically tantamount to the same thing. You add more columns, you're going to need more data. Okay? So in fact, mathematically, this slide and the last one are identical. Okay? Your model and your feature space, they're both the same thing. They are the model. Non-obvious to many. Most people separate data preparation from the actual glamorous gradient-boosted trees or support vector machine. The whole thing is actually the model. Okay. Now, this is just saying, this is not just, okay, many things are actually just fantasies of mathematicians. I can tell you that coming out of the world of academia. But this one is not. More data does actually mean better predictive power for these models as well. And it follows that theoretical growth. Okay, so here, this is orders of magnitude of data. This is on a log scale, as before. This is Gini, which is one measure of predictive power or predictive accuracy. And you can see here, now keep in mind, for many of you who work on these high value or high cost problems, you know 1% improvement in predictive power could be 10 million bucks. Okay, so this is pretty significant. So right away, if you fall asleep right now, I've told you the answer. It is true. Bigger data, better results, better improved dollars by large amounts, potentially. Okay, so, but how else can downsampling the data be harmful? Let's be honest here. How many of you in practice really do downsample the data right now? Come on, more honesty. All of you are downsampling the data, I know it. Okay, why? Because of the computation downstream is usually not able to support really doing the whole thing. Okay, or you just may not have big data. Then you're not downsampling. Okay, but now this one is somewhat non-obvious even to data scientists. Many of you are familiar with cross-validation. Cross-validation is what you should be doing to make sure that you don't overfit the data, or you're trying to make a prediction, so you pretend that you didn't see some of it. And anyway, you make a big loop, and you end up, if you do tenfold cross-validation, you have to make 10 models for every parameter setting in a try. So it's very expensive computationally. So a first thought for many, I would say most, okay, if I have 10 billion rows, I don't really want to pay all that cost. So maybe it's okay if I just take a subsample of that and cross-validate on that subsample. Who thinks that's sort of reasonable? Okay, seems reasonable, perhaps, but it's not, unfortunately. You would really like to be able to do that, but you will make an error. Why? Because of this. The optimal parameters of a model, that's the setting of the knobs, like for gradient-boosted trees, one popular kind of model, there are at least 3 common knobs. One is the number of trees in the model, one is the depth, one is the learning rate. This is showing, this is actually showing arguably the most important parameter, the number of trees, which obviously more trees in this model makes it more complex, which you would expect that as your data size grows, you get finer and finer detail that you can model, and therefore you should use a more complex model. Okay, but most people, many people forget that your model should actually grow. These non-parametric models grow with the size of the data. Okay, in many cases, they're on the same order of magnitude in size as the data. That can be depressing, but it's true. If you really want the best accuracy, that's true. This is showing it grows dramatically. Okay, so because of that, that means if I train with a small sample, I cross-validate to find optimal parameters, I'm finding the optimal parameters of the wrong data size. I cannot then take those parameters and retrain with the whole data set, which is a common thing. Okay, that's kind of a little one for the data scientists. I know it's a little confusing, but the upshot is, if you downsample to do the basic process of machine learning, you're getting the wrong parameters. Bummer, I know. Furthermore, this maybe is more obvious. When you downsample, in many cases, the important data points are too rare to be further reduced. You may have high-interest outliers or small clusters. There may be a small set of teenage customers who spend a huge amount of money. If you throw out data, you're going to miss them. High value, but that's when you're in the discovery phase. You may already know you have examples of a certain kind of fraudulent transaction, but you only have 4 of them, even though you have billions of rows. If you subsample, you're not ever going to find those 4, which may be of a certain kind, and so on. Every data set almost has discrete values, and they're going to be rare values. There's discrete values. Think of things like zip codes and so on. Many data sets have missing values. That means it just wasn't recorded, that cell in the table. We have lots of them in many cases. In that case, you really just don't have as much data as your number of rows and columns purports. So these are just many ways in which you may have a lot of rows and columns, but you still somehow feel starved for data. still wish you had more data. Okay, and for things like speech recognition and so on, these are natural systems with a massive amount of variation, say between speakers. You just never have enough data to train a good general purpose speech recognizer. Okay? Here's another non-obvious one, something that many people do, many data scientists may go, well, I have a rare class like fraudulent transactions, maybe 2% or 0.5% of the data transactions are fraudulent. The rest are normal. But, 99.5% is normal. Surely I can downsample that, and I'll just be fine. I just keep the rare class. Okay, everything I said still applies. So not true that you're not harming yourself there. But furthermore, you're warping your probabilities. And unless you correct them afterward, you have incorrect probabilities in your predictions. There are ways to treat that, but they're not in textbooks. Okay, lastly, you can tell I have, if I were trying to build drama, I would have made this a top 10 list, but I'm working up to 10 points. Last two. So what else should we know that leads us toward some practical best practices? Well, one way of saying it is you have no excuse anymore. There is a way to do machine learning on the whole data. Asterisk with Skytree. So it is now possible to fully train models correctly with very large amounts of data. And this is showing some default type settings of the parameters that people often use. And you can see this is either 5 billion rows or elements, I forget which we do routinely. So it is definitely possible. So furthermore, I said fully trained, correctly trained. You may go, I'm not going to do everything you said. You said, first of all, I need to try a bunch of parameter settings. We would try automatically, let's say, at least 100 parameter settings for each data size on this plot. And furthermore, we should look at the runtime at the optimal setting of the parameters, not the wrong default setting. Okay, which that complexity is growing with the number of data. So this whole thing, I think, is really hard to do, really for real. This is going up by orders of magnitude. This is a log plot, runtime here, and you can see it's still kind of reasonable. It's worse than the last one, but still under control. Okay, finally, this is for those of you who raised your hands when you said maybe it's not always better to use bigger data. And this can be why. Okay, so here are two pictures. This is representing these things that correspond to these errors I showed you. So this is your total error. This is in orders of magnitude. Okay. Now, if your total error in the black, most of it is due to this blue one, which is, if you remember, was your how good is your model type. For example, if your error due to having an insufficient model class, like linear models, like logistic regression. Many of you use logistic regression. I know, you don't have to admit it, but I know it's true. If that dominates, then adding more data won't help, right? Because a simple linear model cannot take advantage of all of the extra detail in the data. It's fitting too simplistic a model. So you can keep throwing data at it. It doesn't matter. Your error due to having not enough data is already low. It's this thing that dominates. Okay? So in other words, your error in this case due to not having enough data is not your biggest problem. So if it's not your biggest problem, then throwing more data is not helping. Okay? So that can be one reason you don't see gains when you add more data because you need to work on your main problem. Use a fancier model that supports more data. Similarly, if your error is dominated by having a crappy optimizer, and there are two senses of that. One is that the optimizer that you think of, like the optimization of a support vector machine, and you use some simple approximation like stochastic gradient descent, which is a common thing in the last 5 years, yes, you will suffer some error. And if it's too much, it dominates, then again, throwing more data at the problem doesn't help you. You need to first use a better optimizer, which is more expensive, which is probably why you did an approximation. Cross-validating over too few parameters is another sense of optimization, poor optimization, incomplete optimization. And that's probably the most common reason that people have this situation. Okay, if you're not doing enough cross-validation on enough parameters, then throwing more data at it won't help. All right, so what do you need to do? You need to, a picture like this, you need to optimize minimize all your sources of error at the same time. Use fancy models, use all the data, use good optimizers, cross-validate with a lot of parameters. Here's a summary. If you want the long version, it's in a 14-page white paper. You can stare at the math and come back and bitterly complain to me about any point. But here they are. Maybe more useful is for you is the practical upshots of this. So training on a subsample, first point, training on a subsample of data is giving up measurable predictive power, which is translates to significant business value in many cases. When your data set contains important rare objects or values, which is actually pretty common, then subsampling can not only be suboptimal, it can be disastrous for the exact type of thing you're looking for, or maybe don't know you're looking for. Training too simple models may block the benefit of bigger data, and performing too incomplete training may block the benefit of bigger data. And the non-obvious one here is you didn't try enough parameters in cross-validation. Okay, and then you may also be leaving accuracy/money on the table by performing cross-validation on a subsample, which should give you the wrong parameters. Roughly speaking, you're getting a an underestimate of the complexity. Okay, you're going to underestimate your how fancy a model you need. Okay, so that's it. When you're ready to max out all of your data's potential with full state-of-the-art ML, come talk to us, and I'll take some questions. Any questions? Yeah?
You use the term simple model, and I think you use linear regression as an example of a simple model. Is it incorrect to assume that if I had a nonlinear relationship, and I applied a linear regression, that would be wrong? It's not, so I guess it's just like if you apply the wrong model, that's bad. It's simple and complex.
It's saying the same thing. You can always fit a linear model when the true function you're trying to fit is nonlinear. In fact, you never really know, right? Nobody tells you the true form of the underlying function.
That would be wrong.
It'd be wrong, but the only way you're going to know that is you're just going to see poorer error, right? And so it's tantamount to saying you need to increase the complexity of your model, and then you'll get better error.
I'm trying to get an understanding. It's not a simple, complex issue. It's you got the wrong model. That's the issue.
I know what you're saying, but it's tantamount to simple, complex anyway, no matter how you look at it, because there's no way you can ever know whether it's wrong or right. All you can do is see what your error is. So it's, in 22 years of doing it, I've never seen it really, really, really linear fit be absolutely the right thing. So linear is almost always wrong. So, but, you know, it's just a matter of how much error you're willing to tolerate. If you want to go cheap on computation, there are reasons to go linear, you know. So, but if error is your issue, then probably you shouldn't go linear. Yep.
Sometimes if you're having a lot of parameters, leads to overfitting of the model. You know, so like we sometimes use the principal component method or some other methods to increase the number of parameters. So, isn't it true that sometimes too much data will also lead to too much overfitting?
Well, it won't cause it in and of itself. Is if you don't do enough optimization effectively to mitigate, to make sure that you have the right complexity, then you will have poor results. So it's really a matter of how much computation. It boils down to computational effort. How much computational effort do you do to make sure you're not overfitting or underfitting? So it's tantamount to, do you try enough parameters to get it right? And do you make sure you do full cross-validation to make sure you're not overfitting? Yeah.
I kind of notice a bit of a catch-22 in the slides, in that you don't want to train your model on a subsample, but you need to, for the purpose of cross-validation, you'd also like to retain some holdout data for that kind of purpose. So can you give some guidance on how you should take that holdout data without reducing the size of your training data?
Yeah, so so the question is basically if you need to prevent this overfitting, you need to hold out some data, which kind of costs you a little bit, because hopefully I convinced you should be training with as much data as you possibly can, but you have to sacrifice some. There's a question to make sure you're preventing overfitting. So that's why we do this tenfold cross-validation thing, which is your standard kind of default approach. You try to use as much as you can in training and hold out a little bit, but then you try to hold out a different little bit and a different little bit, and you average them. The ultimate extreme of that is you do leave one out you leave only one data point out, and then you do that, n-1 times. So there, it's a tricky issue. Yeah. Yep. Yeah. Yes.
So I believe the optimal number of fields are like based upon the predictive power it has on the test data set, right?
Right.
So now my question is, like, you have testing accuracy on your test data set, and your matrix is like accuracy at top n. So is the optimal number of fields still grow with the size of the data, or will there be some change in the way the size of the training set and the optimal number of fields?
Under the situation where you've got like a precision at k kind of metric, yeah, it should be true for any kind of metric. Any kind of metric. Yeah, absolutely. Yeah. Yeah. Other questions? Okay, so is everyone convinced? Bigger data is better, except for a few cases. All right, thanks. See you at the booth.